The average time it takes Amazon to ship a product after it has been ordered is 22 hours. A manager at the Amazon Fulfillment Center in Moreno Valley, California, thinks their average speed is faster. To test this, she tracks 47 packages to see how long it takes to ship. She obtains the following data in hours, and we have the data. Do you think the manager should conclude that the fulfillment center at Moreno Valley does ship items faster? So this is a preview, an introduction to a hypothesis test. It is not a full-fledged hypothesis test, but it helps us get to understand some of the mechanics. So step one, let's state the hypothesis. What is the claim? So the average time it takes Amazon to ship a product after it's been ordered is 22 hours. We want to see if the average speed in Moreno Valley is faster. So the hypothesis is that we're no faster. Okay, so in this case, we're dealing with an average, right? So not a population proportion, but a population mean. And the hypothesis is that the average in Moreno Valley matches the overall average of Amazon to ship a product, which is 22 hours. That's a hypothesis. That's what we're testing. Can we safely conclude, based on the data, that the shipping speed in Moreno Valley is actually faster than the average Amazon time? Step two, determine the features of the distribution of point estimates using the central limit theorem. So we will be doing this assuming that this is in fact the population mean. And then we will determine the likelihood that we get the sample that we do, or something more extreme, and based on that decide whether or not this hypothesis is actually correct. Okay? So by the central limit theorem, we know the point estimates are either normally distributed or t-distributed. So in this case, the point estimates are sample means, because those are estimating the population mean. Now, if we know the population standard deviation, then we can use a normal distribution. But in this case, we do not know the population standard deviation. It does not tell us the population standard deviation. Since we don't know it, we are going to have to estimate it using our best guess, which would be the sample standard deviation. And when we do that, we need to use a less precise kind of distribution, the t-distribution. So because we're estimating the population mean, and because we do not know the population standard deviation, we are going to be using a t-distribution. Okay? The distribution mean of the sample means is the assumed population, because we are assuming that's correct, right? And then the distribution standard deviation, we need to calculate that. It's very similar to what we get from the central limit theorem. So the distribution standard deviation so if so I'll call it sigma x bar. If we knew the population mean, the population standard deviation, it would be sigma, the population standard deviation, sometimes we call it sigma x, divided by the square root of n. But we do not know the population mean. The population standard deviation. So we need to estimate using our sample standard deviation. So whatever this quantity is what we are going to use for the distribution standard deviation. Okay, so that's going to require some work, because we will first need to find the sample standard deviation, and once we find that, then we'll have to divide that sample standard deviation by the square root of n. Okay, so to find the sample standard deviation, we're going to need all this data. Okay, so I'm going to copy it. I'm going to, and this is from a previous problem. Okay, and we're going to paste it in code cell. So paste. Okay, so now I've got the list of that data. Now, if you remember standard deviation, your sample standard deviation, to calculate it, you take x minus x bar, where x is a data value. You square it. You're going to add it together for every single data value. You divide by n minus 1, and then you take the square root of it all. Okay? So that's what we're going to do. Notice, though, that in order to calculate the sample standard deviation, we need the sample mean. So that's going to be our first step. Let's calculate that sample mean. Okay? So let's first find how many elements we have. And then our sample mean will just be all our data added up divided by how many data values we have. And let's print that out. Okay, we'll need that later. That's our sample mean. But now that we have that, we're all set to find our sample standard deviation. So our sample standard deviation, and we could almost copy this exactly. So we're going to start with the x minus x bar. So x minus x bar. Notice I could use x because that's where my data is, right? So my data is in variable x. And then I'm going to subtract my sample mean. Okay, so I'm going to do that for every single data value, and then for every single data value, I square it, right? So that's got me up to here. What comes next? I need to add all that together. So I'm going to take everything I have so far, I'm going to add it together with a sum function. The sum function says, hey, all that list of all that stuff that's in there, I want to add it together. Okay, that's going to give me the whole numerator. The whole numerator. So now I have to divide by n minus 1. So I'm going to take all that, I'm going to divide by n minus 1. I'm going to be careful to put that n minus 1 in parentheses. Without those parentheses, I divide the n first, and then whatever the answer I get from the division, I subtract 1. Now, I don't want to do that. I want to divide by all of n minus 1. So put that in parentheses. And once I have all of this, which is what I have so far, I still need that square root, and I want to square root everything. So I'm going to put a square root function at the beginning, sqrt for square root n, and throw it all in parentheses. Okay, and that is going to give me my sample standard deviation. Okay, now if you remember, what are we trying to find? We're trying to find the distribution standard deviation, which isn't quite the same as the sample standard deviation. The distribution standard deviation is going to be that s divided by the square root of n. So let's go back here, and now that we have our sample standard deviation, we could take that and divide by the square root of our sample size, which I've stored in n up here. Okay, so let's run that. Oh, and of course, I've actually got to print it out. And that is the answer to that next text box. That is the distribution standard deviation. Okay? So it requires a little bit more work when you're using a t-distribution. Now that we're there, we can go on to step 3. So assuming the claim is true, find the probability of obtaining the point estimate. Well, our point estimate is a sample mean, not a sample proportion. Okay? And our best guess is our point estimate, which is our x bar, 21.21. Okay? So what's going on here is we have a t-distribution. Now, a t-distribution looks an awful lot like a normal distribution. We still get that bell curve. We're assuming the mean is 22, right? That's our hypothesis. So we've hypothesized the mean is 22. Our claim is that our sample is 21.21. So 21.21, that's a little less than 22. That's over here. Now, if it were bigger than 22, I'd put it over here, but it's not. So I put it over here, and then the more extreme values are over here to the left. Okay? So because of that, I know I'm going to want a less than or equal to symbol. Because that less than or equal to tells me I want the left tail, the values less than 21.21. Okay? All right. So now that we have that, we want to convert it to use with our distribution. So we know we have a t-distributed data. So that means I'm going to want to find the t-score. And I'm going to use the same symbol, less than or equal to in this case. Okay? And so I'm going to need the t-score of 21.21, and I'm going to put it right here. So the t-score is an awful lot like the z-score. T-score, I'm going to use my point estimate minus my distribution mean over the distribution standard deviation. The big difference is that this now uses the sample standard deviation to estimate it. Okay, instead of using the population standard deviation. And because of that, we're using the t-distribution. Okay, and remember, this is our assumed population mean, where our population mean is, we assume 22. We're hypothesizing is 22. So let's find that t-score. So we're going to have our point estimate, x bar, minus our distribution mean, which is the same as our population mean. Now, I don't have a variable for that yet, so I could just put in 22, because remember, that is what we are hypothesizing the population mean is. I like variables, so I'm actually going to store that 22 in a variable. Makes it a little bit easier for me to read, helps me know where things come from. And then I'm going to divide by that sigma x bar, and I do already have that in a variable. So let's print out that t. And we have a t-score of negative 1.73. Okay. All right, now that we've converted it to a t-score, we're ready to actually find the probability. So let's go here. Since we're dealing with a t-distribution, we're going to use the pt function. We're going to tell it what our t-score is. Remember, for a t-distribution, we also need degrees of freedom. So in this case, degrees of freedom is going to be, degrees of freedom is, well, we have 47 packages we're tracking, so we'll just do one less than that, so it'll be 46. So 46. Or you could just do the sample size minus 1. That's the easy way to do it. It will always work. It will always be n minus 1 for this kind of a hypothesis test. And then we need to set the lower tail. So in this case, the lower tail, if we look at this picture here, we do have the lower tail shaded, right? So the lower tail is true. And that gives us our probability. So what does that mean? That means that if the population mean is 22, so that means if the true average time it takes to ship for the Amazon Fulfillment Center in Moreno Valley is 22 hours, if that's actually what the mean is, there is about a 4.5% chance that we get a sample mean from a sample of 47 packages, that our sample mean is as extreme as the sample mean that we actually obtained. So the question then is, is this so unlikely an event that we think that instead of thinking we just got lucky, we actually think that our hypothesis that the population mean is actually 22 hours is actually false? Or are we not, is this not so unlikely that we're not comfortable saying that? Okay? So in this case, 4.5%, that's a pretty rare event. And a lot of times in statistics, something that's that rare in a hypothesis test, we are comfortable in saying, you know what, this is so rare an occurrence, this is rare enough that we think that instead of thinking that we got lucky and got this rare event, that actually the hypothesis is wrong. We don't think we're that lucky. We just think that our initial hypothesis is incorrect, and that instead of 22, it would actually be a lower number. Okay. So at this point, it's kind of a judgment call. Okay, this is step 4 we're working on here. At this point, it's kind of a judgment call whether or not you think that this is so unlikely that we should reject the hypothesis. Later on, we will learn how to be more exact with this and more careful with this so that it's not up to us to just kind of make our own judgment call. It either is or isn't past some level of tolerance that we are comfortable with. Okay, but at this point, there's not necessarily a right answer. It's what you're comfortable with. If it were me, I'd probably say, this is unlikely enough that I think maybe it's a little less than 22 hours, that the true population mean is less than 22 hours, that the true shipping speed is less than 22 hours. Well, let's submit it. Let's see what we get. And we have it.